In our modern world, we are surrounded by electronics. They are in our homes, our cars, and even in our pockets. These devices have changed our lives. They connect us, inform us, and help us understand the world. But this progress has come at a cost. The devices we rely on are creating a growing mountain of waste. This electronic waste, e-waste, is a serious problem. It pollutes our land and our water with harmful materials. We have created gadgets that last a very long time, long after we've finished using them. Imagine an electronic device that could simply disappear when its job is done. This is not science fiction. It's the promise of a new kind of technology, the biodegradable sensor. A biodegradable sensor is a small, smart device. It can measure temperature, pressure, and the presence of chemicals. Its most amazing feature is what happens afterwards. After finishing its task, it's designed to break down. It can dissolve in water, in soil, or even inside the human body. These devices are made from materials found in nature. Some use polymers from cornstarch like polylactic acid, PLA. Others use simple paper or flexible silk. Even conductive parts can be made from metals our bodies can absorb, such as magnesium and zinc. The goal is simple but profound. Create electronics that perform brilliantly and then return to the environment harmlessly. In this series, we will journey into the world of vanishing electronics. We'll discover what biodegradable sensors are and how they work. We'll look at the clever materials that make them possible. We'll see how they're used, from healing the human body to monitoring the health of our environment. The story of biodegradable sensors is a story of hope. It shows that with creativity and respect for nature, we can build a future where technology serves us without harming the planet for generations to come. At the very heart of every biodegradable sensor is a simple, yet profound, purpose. It is designed to detect a specific change in its surroundings and report back. Think of it as a tiny, temporary scout, sent on a mission to gather a single piece of crucial intelligence. This fundamental function is what makes these devices so powerful, whether they're inside the human body, buried in a farmer's field, or monitoring a delicate ecosystem. The change it's looking for is called a stimulus. This can be a physical event, like a shift in temperature or a subtle change in pressure, or it could be a chemical event, such as the presence of a specific molecule. It could even be a biological signal, like the electrical firing of a nerve. The key is that the sensor is built with a singular focus, designed to ignore everything else and react only to its target stimulus. The part of the device responsible for this initial detection is the sensor element, also known as the sensing layer. This is the most critical component, carefully engineered from special materials that react in a known, predictable way when they encounter the thing they are meant to measure. For example, a temperature sensor might use a material whose electrical resistance changes reliably with heat. A pressure sensor might use a flexible material that deforms under force. Chemical sensors take this specificity to another level. They can be coated with molecules, often antibodies or enzymes, that act like a lock for a very particular key. These receptors will bind only to a target substance, or analyte. A classic example is a sensor for glucose in the bloodstream, crucial for managing diabetes. But this same principle can be applied in environmental science to create sensors that detect specific pollutants like heavy metals or pesticides in a river, even at incredibly low concentrations. Once the sensor element has detected its stimulus, a critical translation must occur. The physical deformation, the chemical binding, or the temperature change must be converted into a language that electronics can understand. This process is called signal transduction, and it's the bridge between the physical world and the digital one. The component that performs this magic is the transducer. It acts as an interpreter, taking the raw, non-electrical response from the sensor element and turning it into a quantifiable signal, most often an electrical one. It's the link that allows a biological or chemical event to be read by a computer. This electrical signal, a change in voltage, a fluctuation in current, or a shift in resistance, is now a piece of measurable information. It is clean, digital data. This data can then be processed, recorded locally, or transmitted wirelessly for us to see and analyze on a smartphone, a doctor's monitor, or a scientist's computer. Imagine a sensor monitoring soil moisture for a farmer. The sensor element is made of a biodegradable polymer that absorbs water, causing it to swell. This physical swelling puts pressure on the transducer. The transducer then converts this pressure into a change in electrical resistance. When the soil is dry, the material is compact and the resistance is high. As the soil becomes wet, the material swells and the resistance drops. This simple change allows for precision irrigation, saving water and improving crop yields. The defining feature of a biodegradable sensor is, of course, its ability to vanish. This is not a random process or a sign of failure. It is a precisely engineered feature, a programmed and controlled end to the device's life, known as transient behavior. The materials are chosen not just for their sensing properties, but also for their predictable rate of degradation. This disappearance is triggered by the sensor's own environment. The most common and universal trigger is water, which is present in the body, in soil, and in the atmosphere. Beyond water, other triggers can be used to fine-tune the sensor's end of life. Some materials are designed to break down in the presence of specific enzymes, while others might be sensitive to changes in pH or even light. The primary mechanism for this breakdown is hydrolysis. Hydro refers to water, and lysis means to break apart. In this chemical reaction, water molecules act like molecular scissors, attacking the bonds that hold the long polymer chains of the sensor's material together. Over time, these long chains are snipped into smaller, water-soluble pieces that can be safely absorbed by the body or the environment. The second key mechanism involves enzymes. Enzymes are biological catalysts, highly specialized proteins that accelerate chemical reactions. In this context, they act like a dedicated molecular cleanup crew, targeting and dismantling the sensor's materials. This enzymatic degradation is often much faster and more specific than simple hydrolysis. To see how these principles come together, let us imagine a specific, real-world application. A biodegradable sensor designed to monitor the pH level of a healing surgical wound. After an operation, keeping the wound environment stable is critical for preventing infection and promoting recovery. A change in pH is often one of the earliest and most reliable signs of trouble. If pathogenic bacteria begin to colonize the wound, their metabolic activity can cause the local environment to become more acidic. Our sensor is designed to detect this specific chemical stimulus. The sensor's pH-sensitive material reacts to the change in acidity, and the transducer converts this into an electrical signal. This data is then transmitted wirelessly to an external monitor, giving the clinical team a precise, real-time reading without ever needing to disturb the wound dressing. This early warning allows for prompt intervention, heading off a serious infection before it takes hold. After a few weeks, once the healing process is well underway and the risk of infection has passed, the sensor's job is done. Triggered by the body's natural fluids, hydrolysis and enzymatic action begin to break it down. The materials degrade into harmless biocompatible byproducts that are simply absorbed by the surrounding tissue. Within a couple of months, nothing is left. The sensor has performed its vital monitoring task and then, as designed, simply faded away, leaving no trace behind. The foundation of many biodegradable sensors is built from a remarkable class of materials known as biodegradable polymers. Think of them as long chains of repeating molecular units, meticulously designed not just for strength and flexibility, but with a built-in clock. When their time is up, these chains are engineered to break down into simple, non-toxic components that the environment, or even the human body, can easily absorb. This ability to perform a task and then gracefully disappear is what makes them so revolutionary. Two of the most important of these are polylactic acid, or PLA, and polycaprolactone, known as PCL. PLA is a workhorse in the world of bioplastics, often derived from renewable resources like cornstarch or sugarcane. It's a rigid, transparent material, similar in feel to conventional plastics. You might have already encountered it in compostable food containers or 3D printing filaments. For sensors, this rigidity is a key asset, providing a stable, protective housing for delicate electronic components. When it degrades, it breaks down into lactic acid, a compound our bodies produce naturally during exercise. PCL, on the other hand, offers a different set of talents. It is a much softer and more flexible polymer, with a texture almost like rubber. This pliability is crucial where a device needs to bend, stretch, and conform to irregular shapes without breaking or causing irritation. This makes it ideal for medical implants that sit within soft tissue or wearable sensors that must move with our skin. The true genius lies in combining them. By strategically using both PLA and PCL, engineers can create hybrid structures that are strong where they need to be and flexible where they must bend. Furthermore, because PCL degrades more slowly than PLA, designers can create devices that dissolve in stages, all programmed with a finite lifespan. While modern chemistry gives us powerful tools, nature often holds the most elegant solutions. For thousands of years, humans have admired silk for its beauty and strength. Today, scientists have rediscovered its power by looking at its fundamental building block. By carefully processing silk cocoons, they can isolate the core protein, fibroin, and reform it into incredibly thin, transparent, and flexible films. What makes silk fibroin extraordinary is its biocompatibility. It is so well tolerated by the body that it can be placed in direct contact with our most sensitive tissues, even the delicate surface of the brain, without causing a harmful immune reaction. This opens the door for implants that can safely monitor neural activity and then dissolve away. This unique combination of strength, flexibility, and biocompatibility makes it a perfect substrate for ultra-thin, flexible sensors that can be worn like a temporary tattoo. These epidermal electronics move and stretch with the body, gathering precise data without the wearer even noticing they are there. But perhaps its most remarkable property is its precisely tunable relationship with water. By adjusting the crystalline structure of the fibroin protein, scientists can program exactly how fast it dissolves. A sensor can be designed to last for days or weeks, and then, when its job is done, wash away with simple water, leaving no trace. In the search for advanced materials, it's easy to overlook one that has served humanity for 2,000 years. Paper. Made from cellulose fibers, paper is abundant, cheap, and naturally biodegradable. By using standard inkjet printers loaded with special conductive inks, researchers can create circuits, electrodes, and sensors directly on paper for a fraction of the cost of traditional methods. This makes it a game changer for low-cost diagnostics in remote areas or for monitoring freshness in food packaging. Now, imagine a material that is mostly water, yet can be engineered to perform complex tasks. This is the strange and wonderful world of hydrogels. These are three-dimensional networks of polymers that can absorb and retain enormous amounts of water, becoming soft, squishy, and very similar to living tissue. Their porous, tissue-like nature makes them excellent for interfacing with the body, but their most exciting feature is their ability to be smart. They can be designed to respond to specific environmental triggers. For example, a temperature-responsive hydrogel can be loaded with medicine and designed to shrink and release its payload only when it detects a fever. Others can be engineered to respond to changes in pH or the presence of a specific molecule, acting as both sensor and actuator in one. Of course, for any electronic device to function, it needs materials that can conduct electricity. For a device designed to disappear inside the body, traditional conductors like copper or gold are non-starters. The solution comes from a surprising source: essential minerals that our bodies already know and need, primarily magnesium and zinc. Magnesium is a particularly promising material for these transient electronics. It's a lightweight metal that conducts electricity well. Crucially, it reacts with the body's natural fluids in a predictable, controlled corrosion process. As it degrades, it slowly releases magnesium ions, an essential nutrient that the body can easily absorb and use for metabolic functions. Zinc offers a similar set of advantages. It's another essential nutrient, vital for immune function and wound healing. In the context of bioresorbable electronics, zinc tends to degrade more slowly and steadily than magnesium. This difference in corrosion rates is a powerful tool for engineers, allowing for a staggered degradation where different parts of the device vanish at different times in a carefully choreographed sequence. By combining these conductive metals with substrates like silk or PLA, engineers can construct entire electronic systems that are fully biodegradable. An implantable device built with these materials can monitor a patient's recovery after surgery, transmitting data wirelessly, and then, once its mission is complete, simply be metabolized, becoming part of the very body it was designed to help heal. Perhaps the most profound and immediate impact of biodegradable sensors is found within the realm of medicine. For decades, medical implants have come with a significant drawback: the need for a second surgery to remove them once their job is done. This follow-up procedure carries its own risks, costs, and recovery time. But what if the implant could simply vanish when no longer needed? This is the future these vanishing devices offer, a future where healing is monitored with incredible precision, without the burden of removal. Take, for example, the critical hours and days following a traumatic brain injury or complex neurosurgery. Monitoring intracranial pressure is vital to prevent further damage. Traditionally, this involves wired sensors that create a potential pathway for infection and must be surgically removed. Now, imagine a biodegradable pressure sensor, no thicker than a human hair, placed inside the skull. It wirelessly transmits its vital data for the few crucial days or weeks of recovery, then simply dissolves away into harmless byproducts, eliminating the need for a risky second operation. Chronic conditions like diabetes could also be revolutionized. The daily routine of finger prick tests can be painful and provides only a snapshot in time. Researchers are developing biodegradable biosensors that could be implanted just beneath the skin, tracking glucose levels continuously and in real time. This device would function for several months before safely breaking down, offering a more complete picture of a patient's metabolic health and enabling more personalized, effective treatment with far less discomfort. The benefits extend to routine diagnostics as well. Temporary ECG patches made from paper-based electronics can monitor a patient's heart for a few days, perhaps after a minor cardiac event, or to check the efficacy of a new medication. Once the monitoring period is over, the entire patch can be discarded without creating hazardous e-waste, a growing problem with conventional disposable medical electronics. Beyond the human body, biodegradable sensors offer a transformative solution for monitoring the health of our planet. Current environmental monitoring is often expensive and sparse, relying on a few fixed stations to measure vast areas. Biodegradable sensors change this paradigm entirely. They can be deployed in large numbers, like scattering seeds from a drone, to create widespread, high-density sensor networks that provide a far more detailed and dynamic picture of an ecosystem. Consider monitoring a large river system for agricultural runoff or industrial discharge. Thousands of tiny, inexpensive sensors could be released upstream. If a sensor detects a pollutant like a nitrate or a heavy metal, it could trigger a color change or transmit a simple wireless signal. By tracking where these signals originate, authorities could pinpoint the exact source of pollution in real time, rather than discovering the problem miles downstream, long after the damage is done. In agriculture, where soil health is paramount, these sensors could provide hyper-localized data on moisture levels, pH, and nutrient content. This enables true precision agriculture, where water and fertilizer are applied only when and where they are needed, root by root. This not only conserves precious resources and prevents harmful runoff, but also maximizes crop yields. And the best part? There is no cleanup. At the end of the season, the sensors simply break down, enriching the soil with organic matter. They become part of the very ecosystem they were designed to help, completing a perfect, sustainable cycle. This concept of temporary, functional electronics extends to the vast network we call the Internet of Things, or IoT. The current vision of IoT involves billions of permanent powered devices, creating a colossal stream of future e-waste. Biodegradable sensors offer a more sustainable path forward, the ephemeral internet, where connectivity exists only for as long as it's needed. Think of logistics and shipping. A temporary RFID tag built on a paper substrate could be attached to a parcel to track its journey through the supply chain. Once the package reaches its final destination and is unboxed, the biodegradable tag could be composted right along with the cardboard box, leaving no trace. Or imagine a fitness patch designed for a single event like a marathon. It could monitor your heart rate, hydration, and electrolyte levels in real time. After you cross the finish line, instead of peeling off a plastic and metal device bound for landfill, you could simply wash it off in the shower, where it dissolves harmlessly down the drain. Perhaps one of the most practical everyday applications is in biodegradable smart packaging, which aims to solve the massive problem of food waste. Static best buy dates are often overly cautious, leading consumers to throw away perfectly good food. These sensors provide a real, dynamic assessment of food quality. They offer an honest label that tells you the true state of the food inside. For instance, a sensor integrated into a package of chicken could be designed to detect volatile compounds like ammonia that are released as meat begins to spoil. As the concentration of these gases increases, the sensor would change color, from green to yellow, and finally to red, providing a clear, intuitive, and unmistakable signal to the consumer that the food is no longer safe to eat. Because the sensor itself is biodegradable, it doesn't add to the problem of packaging waste. The entire package, sensor and all, can be placed in a compost bin. It returns to the soil without leaving behind any toxic electronic residue, closing the loop on a truly sustainable system from farm to fork to earth. The most celebrated advantage of biodegradable sensors is their profound and positive impact on our planet. By design, they are meant to disappear, fundamentally shifting the life cycle of electronics to a circular one. The ability to place a sensor inside the body that safely dissolves after use is revolutionary. It completely eliminates the need for a second surgery to remove an implant. Furthermore, these sensors are often designed to be incredibly flexible and lightweight, allowing them to conform to complex and delicate surfaces. Another key advantage is the customizable lifespan. Scientists can precisely engineer a sensor to last for a specific duration, ensuring the technology provides value for exactly as long as it is needed and no longer. While the benefits of biodegradable sensors are clear, their transient nature also introduces certain limitations. One of the most significant trade-offs is their operational lifetime. Another challenge relates to electrical performance. The materials chosen for their biodegradability do not always possess the same high-performance electronic properties as traditional materials, which can limit the speed and complexity of the circuits. Designers must constantly balance the need for degradation with the demand for reliable and accurate data. This balancing act is at the heart of designing for transience. The very characteristic that makes biodegradable sensors so brilliant can also be a significant limitation. If a sensor is exposed to triggers like water prematurely, it can begin to degrade before its job is finished. To combat this, encapsulation layers protecting active components must be carefully engineered. They must act as a barrier for a precisely controlled period before allowing the degradation process to begin. This sensitivity also affects storage and handling. Unlike conventional electronics, biodegradable sensors may need controlled storage conditions to prevent on-shelf degradation. While the science is advancing rapidly, bringing these innovations from the laboratory to the wider market presents significant hurdles, primarily related to cost and scalability. Navigating the regulatory landscape is also critical. These sensors are a new class of technology, part device and part drug, and may face complex, lengthy regulatory pathways. Ultimately, success depends on earning the confidence of doctors, patients, farmers, and consumers. This is achieved with transparent, peer-reviewed science and robust, independent verification. We have journeyed through the remarkable world of biodegradable sensors, from understanding what they are to how they work and the wondrous materials that make them possible. It is a fundamental rethinking of how we build technology. Instead of creating things to last forever, we are learning to forge a future in impermanence. In one fascinating example, researchers have developed biodegradable sensors that dissolve completely in water after monitoring crops, leaving nothing behind, effectively turning electronics into plant-friendly dirt. The story of biodegradable sensors is a story of balance, balancing function with finitude, performance with sustainability, and innovation with safety. As we look toward the horizon, the field of biodegradable electronics is ripe with possibility. Future research will focus on refining the performance and expanding the library of materials. The vision is a world where fabricating a disposable water quality sensor is as simple and inexpensive as printing a newspaper. The ultimate promise of biodegradable sensors is one of harmony. It is a promise that we can continue to benefit from the incredible power of electronic monitoring without burdening our planet with perpetual waste. The simple takeaway from our journey is this: for a long time, we have built things to last. Now, we are learning the wisdom of building things that do not. The future of electronics, it seems, may lie in its ability to disappear.